Space seems to us to be empty and dark. However, the Milky Way is filled with countless objects of all kinds, from barely visible asteroids to giant star clusters. Each of these celestial bodies is unique in its own way, but in some cases, the combination of chance and the laws of nature generate truly bizarre and anomalous structures, and this means that it's time to embark upon another fantastic journey into the depths of boundless space. First, we will travel hundreds of light years to reach a truly remarkable cosmic object, a unique binary pulsar, a genuine testament to the truthfulness of the laws of relativity. Then we will set out on a long flight through the immediate vicinity of the solar system in search of the most bizarre cosmic structures and anomalies. Next, the journey will take us to the most unusual and sometimes even frightening exoplanets that astronomers have discovered so far. Right after that, we will visit several of the most favorable and Earth-like worlds that could hypothetically support life. Finally, we will travel hundreds of light years to exit our galaxy and plunge into the bottomless darkness of giant areas of empty space, supervoids. Let's get ready, and we begin. First outer space. 3,200 light-years from Earth. The constellation of Puppis. Distant past. The lives of two red giants are coming to their end. Before our eyes, one of them is making a transition to a new stage of stellar evolution. The fuel in its interior is almost depleted, and the star is beginning to cool rapidly. The delicate balance between the forces of gravity and the fury of a thermonuclear explosion is irreversibly disturbed. Trillions of tons of stellar matter start to get unstoppably attracted towards the center of the star. This process unleashes the uncontrolled thermonuclear fusion reaction in the star's interior again. The powerful explosion rips the star apart, leaving a super-dense core in the center, which is red-hot at incredible temperatures. The force of the shock wave irreversibly changes the structure of the stellar matter, destroying its atoms completely. They're compressed into a super-dense matter, generating countless neutrinos. There remains a tiny but extremely massive clot of matter in the place of the destroyed giant. Around it, the outer shells of the former star explode in a tremendous cloud, turning into a scattered gas nebula. These collide with another red giant nearby at a great speed. This causes this other star to flare up like its companion, which has just ceased to be. And when the echoes of the double supernova dissipate in space, only a pair of mysterious objects remain, almost invisible against the vast emptiness of space. This is how a big catastrophe produces extremely rare and unusual cosmic objects, which we call neutron stars. At present, only a few thousand celestial bodies of this class have been discovered, a minuscule number compared to ordinary stars. And to understand why they are so rare, we need to study the evolutionary paths of stars. According to today's concepts, the life of any star is determined almost exclusively by its mass, with a star's mass being less than 8 solar masses. Having completed several evolutionary stages, it eventually turns into a white dwarf. It is assumed that after billions of years, it will lose the rest of its energy and transform into a hypothetical object called a black dwarf. This path is destined for more than 99% of the universe's stars, including our Sun. If the mass of a star exceeds 8 solar masses, however, its evolution follows a different path. eventually resulting in a supernova explosion. The outer shells of the star are scattered in the surrounding space, forming a scattered gas nebula. At the center of the system, there remains a supercompact and extremely dense object, the former stellar core. Its fate also depends entirely on its mass. If it is too great, the core of the dead star will not be able to resist the inexorable gravity and will inevitably shrink into a black hole. However, there is another way. In the case where the mass of the stellar remnant is within the range of 1.4 to 2.2 solar masses, a neutron star is formed. Gravitational forces in its interior destroy atomic nuclei, forming a super-dense neutron matter with rather bizarre physical properties. For a number of reasons, neutron stars are extremely difficult to observe and study. Firstly, celestial bodies of this class are extremely rare. According to calculations, there is only one such object per 1,000 ordinary stars. Secondly, they are very compact and practically do not emit light in the optical range. Therefore, before the advent of X-ray telescopes, it was impossible to spot these objects. Not surprisingly, the first neutron star was discovered only in 1967, several decades after the theoretical justification of their existence. This is largely due to an unusual phenomenon associated with the law of momentum conservation. Thanks to this effect, most neutron stars have a very high rotational speed, and the interaction of their magnetic and electric fields generates powerful bursts of radiation, repeated with a very clear periodicity. Such objects are called pulsars, and they make up the majority of neutron stars discovered so far. Their pulses are effectively detected by X-ray telescopes even at distances of thousands of light years. In total, more than 3,200 neutron stars have been discovered so far, and about 90% of them are single objects. The rest are part of binary and multiple systems. Most often, the companion of these cosmic bodies is a red giant or a main sequence star, but in isolated cases, another neutron star. This happens when two similar stars synchronously approach the end of their life cycle, and the explosion of one of them triggers the collapse of the second. Because of the loss of energy during the transformation, the remnants of stellar nuclei closely converge, which causes their mutual velocity to grow to enormous values. And according to today's concepts, this is how the amazing system called PSR J0737-3039 was formed. It is located at a distance of about 4,500 light-years from Earth, and is quite unique, being made up of even two pulsars located very close to each other. The first of them is 34% more massive than the Sun and has an incredible speed of its proper rotation. Every second, the object completes 44 revolutions around its axis. The second pulsar is a little smaller and slower. Its mass is 1.25 of that of the Sun, and the rotation period is 2.77 seconds. If we want to take a closer look at these objects, we will see that their size is extremely small by space standards. Either component of the system is no more than a couple of dozen kilometers in diameter. As for their mass, it is actually comparable to that of most known stars. Due to these factors, the density of the matter that the pulsars are made up of is extremely high, and in order to understand this question, we need to look into their interior. The use of mathematical modeling techniques, combined with the theory of neutron star structure, allows us to learn even things not immediately visible. The outermost layer of objects of this class is the atmosphere, Incidentally, however, for neutron stars, this concept differs significantly from the familiar sphere of gas a planet is enveloped in, like that of Venus or the Earth. For both components of the system we're looking at now, this layer is no more than a few millimeters thick. This situation is typical for the absolute majority of neutron stars, but the youngest and hottest objects of this class may have an atmosphere of several dozen centimeters. It's made up of plasma, highly ionized remnants of stellar matter. Most of it is hydrogen and helium atoms, but heavier elements are also to be found. The next layer is the outer crust, which can be several hundred meters thick. The gravity in this region is not strong enough to overcome the electrostatic repulsion between electrons and protons, but it is enough to destroy the usual structure of matter. Elementary particles are all jumbled together, but still retain their internal integrity. Several powerful forces are pulling on the outer crust at once, such as gravity, magnetic field, electrostatic repulsion, and centrifugal inertia. This combination places the surface of neutron stars under constant mechanical stress. Occasionally, it builds up to a point where starquakes occur, titanic deformations of the surface of the cosmic object. As a result, there form mountains a few millimeters high and cracks up to a centimeter wide. These numbers do seem insignificant, but at extremely high gravity, a centimeter-high mountain is comparable to Olympus in the conditions of Mars. If we go still lower, we will see that this layer has no clear boundaries and goes several kilometers deep into the neutron star. As we dive into its interior, the pressure gradually increases, causing more and more electrons to be pushed into the atomic nuclei, initiating a reaction with protons. As a result, a neutron is formed, as well as a highly evasive particle called neutrino, which almost immediately leaves the interior of the celestial body, taking excess energy with it. In turn, beneath the inner crust, there lies the outer core, which consists entirely of neutron matter. This amazing substance is a multitude of tightly compressed neutrons, and its density is 10 to 15 times higher than that of the atomic nucleus. For example, our planet, compressed to the same degree, would have a radius of only 150 meters, and a cubic centimeter of its volume would contain several billion tons of neutron matter. In both components of the system we're looking at, the outer core continues as far as the center of the object. Incidentally, particularly large neutron stars should also have an inner core, according to today's concepts. Its structure is still a subject of scientific debate. According to one hypothesis, the pressure in the center of massive stars can be so great that it is capable of destroying even neutrons, forming a hypothetical quark matter. Such an object is called a quark star. Other assumptions allow for the formation of hyperonic or kaon nuclei, consisting of some bizarre matter with highly unusual properties. However, all these amazing structures are still within the domain of hypotheses, and to prove or disprove their existence is not yet possible. If we look at the system as a whole, we will discover several surprising and intriguing facts. First of all, we can notice that according to calculations, the pulsars in this system are moving rapidly around a common mass center along moderately elongated and very compact orbits. Observations show that the average distance between the components is only 800,000 kilometers, which is almost half the diameter of the Sun. Because of this small distance, the speed of mutual motion of both objects is very high. It exceeds 300 kilometers per second, so the pulsars make a complete revolution around a common mass center in just 2.45 hours. Such rapid motion causes a number of unusual phenomena due to the effects accounted for by the theory of relativity. For example, observations show that at the moment of maximum convergence of the pulsars, the period of proper rotation of each of them temporarily increases by 0.38 microseconds, after which it returns to the previous values. Even though this effect cannot be explained from the point of view of classical physics, the theory of relativity predicted it long before its practical detection. This anomaly is associated with the relativistic time dilation, which becomes the strongest exactly at the moment of maximum convergence of objects. Another phenomenon that stands out occurs during mutual eclipses and is associated with an anomalous redshift detected in the spectrum of one of the pulsars. The point is that the gravity of the component closer to us interferes with the signal from the distant object passing by it. Because of this, the radiation loses energy and its wavelength increases. It is also known that the orbits of these celestial bodies are affected by their interaction. This is reflected in the fact that the point of their maximum proximity, called the periastron, is constantly shifting. This phenomenon is called relativistic shift and has long been known to astronomers. It is usually recorded when studying fast celestial bodies. For example, Mercury's orbit shifts by 43 arcseconds every 100 years. As for the periastron of the binary pulsar, it shifts 140,000 times more strongly. Within a year, it deviates from its previous position by as much as 17 degrees. Thus, PSR J0737-3039 has the highest relativistic shift among all stellar systems known so far. If we leave the dry figures for a moment and think about hypothetical planets that may be hiding in this amazing system, their existence seems rather unlikely, but still possible. Some objects, far from the center, did have a chance to survive the crushing double explosion of the supernovae, while others may have formed later. It is still harder to answer this question due to the fact that none of the widespread methods of searching for other planets are effective for exploring such systems. In any case, we cannot speak of the viability of the hypothetical celestial bodies of this system. The freezing cold and deadly radiation make them extremely inhospitable places. Observations show that this binary pulsar is constantly generating gravitational waves, causing the distance between its components to steadily decrease by 7 mm every day. This phenomenon occurs in all physical multiple star systems, but is usually too faint to be measured with any degree of certainty. This tells us that in about 85 million years, the pulsars will merge together to form a black hole. The tremendous cataclysm will be the source of super powerful gravitational waves that will travel through the entire Milky Way and reach other galaxies far beyond it. And the flash accompanying the merger may briefly become one of the brightest stars in the Earth's sky. In any case, the echoes of this devastating explosion will eventually fade without a trace in the infinity of the universe. By galactic standards, the area of space on the outer edge of the solar system is considered to be sparsely populated by both stars and other space objects. Still, approximately 50 stellar systems are known to be located within the radius of 15 light-years from the Earth. Some of them are single stars, while others contain 2 components and more, which is why the total number of stars in this area reaches 65. Many of them have exoplanets and protoplanetary disks made up of gas and dust, where celestial body formation processes are still in progress. In order to analyze this great variety, we'll have to map out the environs. As we slowly recede from our home planet, we will cover dozens of light-years of space and visit quite a few remote worlds. It is time to set out to to the stars. Having traveled 6 light-years away from the Sun, we will reach our first stop, a small red dwarf, designation GJ699, also known as Barnard's star. It is remarkable for its incredible travel speed across the sky, and also for the fact that it's capable of crossing the lunar disk in the course of 180 years. This is due not only to its close proximity to us, but also to its great proper motion. Barnard's star is moving towards the solar system at a speed of slightly over 100 kilometers per second and is going to become our closest star in about 10,000 years. By then, the distance between Barnard's star and our Sun will be just 3.8 light-years. But the red dwarf is so dim that it will not be visible even at such a small distance, and it will be possible to observe it only through optical devices. The star's mass is just 17% that of the Sun, and its radius is 6 times as small as that of our star. Just like all red dwarfs, Barnard's star is quite cool, with a surface temperature just 3,134 Kelvin, or slightly under 2,900 degrees Celsius. With these characteristics taken into account, it isn't surprising that the object's luminosity is 2,300 times lower than that of our parent star. In 2018, the results of a 20-year observation of the star's proper motion were published, which may provide evidence for the presence of an exoplanet nearby. The calculations show it to be a cold super-Earth with a mass of not less than 3.2 times that of the Earth. The planet, named GJ699b, is located about 0.4 astronomical units from the center of the system and takes 233 days to complete a full orbit around its parent star. Unfortunately, the exoplanet follows an orbit that does not lie between the Earth and its parent star, so it's hardly feasible to carry out spectral analysis of the object. Still, mathematical modeling may give us some insights into what it's like. As Barnard's star is very dim, its planetary companion receives 50 times less energy than does the Earth from the Sun. That is why the temperature on the celestial body's surface is extremely low, just 105 Kelvin or 168 degrees Celsius below zero. However, it cannot be ruled out that tidal disturbances or radioactive decay may have released enough energy in the planet's interior to form a warm subsurface ocean. If that is the case, the potential life in its depths would have had ample time to gradually develop. For among the known stars, Barnard's star appears to be one of the oldest. According to estimates, its age is over 10 billion years, which is only a fraction of the expected lifespan of a star. As it is located quite close and is moving in a favorable direction, Barnard's star is one of the highest priority objects for a potential interstellar flight. Time will show if spacecraft launched from Earth will ever reach it. Meanwhile, on the other side of the Sun, there lies the almost exact opposite of the dim red dwarf. Of course, we're talking about Sirius, the brightest star in the night sky, which is 8.6 light-years away from our planet. From Earth, the star appears to be a single light source, but close inspection revealed that it is not a single object, but a binary star. The two components of the system are currently at their maximum distance from each other, about 30 astronomical units. The main star, also called Sirius A, is a bright blue and white star with a mass 2 times that of the Sun. At the same time, it is about 70% larger in diameter, and its surface temperature reaches 10,000 Kelvin. Because of this, Sirius A emits 25 times more energy than our Sun. The second object, known as Sirius B, is barely visible against the background of its bright and massive companion. It is a white dwarf with a radius of about 6,000 kilometers and a mass very close to that of the Sun. Like all stars of this type, its surface temperature is extremely high, reaching 25,000 Kelvin. However, due to its small size, this white dwarf is about 1,000 times dimmer than its stellar companion. After long and persistent research, no signs of planets have been found in the vicinity of Sirius. The reason for this may lie in the comparatively young age of the stellar system, or else the special position of the ecliptic plane. Because of this, the hypothetical exoplanets do not pass between the light source and the Earth, and therefore cannot be detected by the transit method. Another hypothesis claims that Sirius B exhausted its stellar fuel supply roughly 120 million years ago and transformed into a red giant. Soon afterwards, it shed its outer layers, turning into a compact and very hot white dwarf. As a result, the protoplanetary gas and dust disk enveloping the young stellar system at the time was destroyed by this explosion, its remnants scattered into the space around, denying the forming planets any chance of survival. Currently, both components of the system are moving around a common mass center in moderately elongated orbits, completing one every 50 years. Over the next 60,000 years, Sirius will gradually approach Earth, becoming brighter and more visible in the night sky. The minimum distance between us will be about 7.5 light years, after which the system will start to slowly drift away from us. Things will go on like this for about another 660 million years, after which Sirius A will meet the same fate as its companion. For a brief moment, a massive flare will boost its luminosity by a factor of thousands, but within a few months, the star will fade completely, vanishing from the sky forever. Leaving the vicinity of Sirius, permeated by lethal ultraviolet radiation and stellar wind, we will perform a maneuver near the solar system to reach a small star 14 light-years from the Earth. It is designated differently in different catalogs, and one of its names is Wolf 1061. The star is a red dwarf with a radius of about 30% that of the Sun. Its mass is about 4 times smaller than that of our star, and its surface temperature is 3,272 Kelvin, or about 3,000 degrees Celsius. Like all objects in its class, Wolf 1061 is extremely dim. Its luminosity is only 0.14% that of the Sun, so the star is not visible to the naked eye from Earth. However, this red dwarf has one of the most abundant and diverse planetary environments of any stellar system near us. As many as 3 exoplanets have been discovered in its vicinity, all of them rocky and similar in composition to Earth. But still, conditions on each of the 3 celestial bodies differ considerably. The first and closest exoplanet to the parent star is called Wolf 1061b. It is located 0.038 astronomical units from the center of the system and completes a full orbit around it roughly every 5 days. The object has a mass in the range of 1.5 to 2 Earths, and a radius 20% greater than that of our planet. It is likely that the celestial body is tidally locked and faces its star with one side at all times. For this reason, the temperature on the day side of the planet is extremely high, and the flares and stellar winds of the star so close to it virtually rule out any chance of there being an atmosphere. All these factors make the exoplanet completely unsuitable for the genesis and support of life. The second object in the system, Wolf 1061c, is located 0.089 astronomical units from its star and completes a full orbit around it roughly every 18 days. Thus, it is within the habitable zone of the star and can be considered a potentially habitable celestial body. Wolf 1061c is about 3 to 4 times more massive than our planet and belongs to the class of super-Earths. Observations show that its radius is about 1.6 times that of Earth, while the gravity on its surface is calculated to be 60% higher than what we're used to. The exoplanet receives noticeably less energy from its star than the Earth does from the Sun, so its temperature of equilibrium is much lower. It is 223 Kelvin, or about 50 degrees Celsius below zero, which is slightly higher than on Mars. Nevertheless, given variations in temperature during the day and from season to season, liquid water may well exist on the surface of the celestial body, With a dense atmosphere with a pronounced greenhouse effect, this probability is even higher, and conditions on the planet could approach favorable ones. Of all the potentially habitable exoplanets known to date, Wolf 1061c is one of the closest, ranking 5th on the list. The third object in the system is called Wolf 1061d. It follows a clearly elongated orbit, with the distance between the parent star and the aphelium reaching 0.73 astronomical units. As for the perihelium, it lies much closer to the system's center, just 0.21 astronomical units away. It takes the celestial object about 217 Earth days to complete a full year rotation. The mass of Wolf 1061d is calculated to be roughly 7.7 times that of our Earth. If this celestial body turns out to be a rocky object, its radius is supposed to measure about 1.7 times that of the Earth. If, on the other hand, this planet falls in the category of mini-Neptunes with a thick multilayer atmosphere, its diameter is supposed to be not less than 2.2 times that of our planet. In spite of a comparatively high eccentricity of its orbit, Wolf 1061d never enters its star's habitable zone. The celestial body is likely to be completely unsuitable for supporting life, but may pose a great scientific interest in terms of planetary evolution. This system is one of top priority destinations for future explorations, and it is highly probable that there are new discoveries to be soon made in it. In addition to everything else, the star Wolf 1061 is also remarkable for its position, which is virtually at the very edge of the so-called local interstellar cloud. It is an area in space filled with hot but extremely rarefied hydrogen. Its temperature measures about 7,000 Kelvin, and on average there is just 0.3 of an atom to be found in 1 cubic centimeter of space here. It is about twice as little as the average value in the Milky Way. The solar system has been moving through the local cloud for the past 10,000 years. Its average diameter is about 30 light-years, but our system is almost at its very edge. Alpha Centauri, for example, is already in the neighboring so-called G-cloud. We, on the other hand, will spend about another 2,000 years within our cloud, after which we will enter an even thinner and hotter region. The local interstellar cloud was formed by the collision of two giant bubbles of hot cosmic gas. It has a momentum of its own, which is perpendicular to the direction of the solar system's motion, and also has a magnetic field and radiation. Fortunately, despite the high energy of the interstellar gas particles that make up the cloud, there is no threat to organisms on Earth. The solar wind is a reliable protection against cosmic hydrogen, and the Earth's dense atmosphere takes the hit of particles that do break through the heliosphere. Still, traces of the isotope iron-60, also called interstellar iron, have been found in the ice of Antarctica. It is thought to have arrived to Earth from no other place but the local interstellar cloud. As we continue our journey through space, we will soon get to a rather unusual star called AP Columbae, located 27.4 light-years away from Earth. First and foremost, it draws our attention because it was born just 40 million years ago, when the dinosaurs would have long since died out on our planet. What is even more striking is that its birth took place in a completely different region of the galaxy, 450 light-years from the object's present position. Young stars usually remain close to their stellar nursery for quite a long period of time, up to several 100 million years. If you analyze the movement of AP Columbae, however, you will find that it probably previously belonged to the open cluster IC2391. The cluster has about 30 stars, united by a common origin and direction of movement. But a few million years ago, one of them exploded, shattering the delicate equilibrium of a multitude of cosmic bodies. This catastrophe gave the young star an additional momentum that swiftly expelled it from its birthplace. a very small red dwarf with a mass just 13% that of the Sun, this star emits 4 times more energy than any other known celestial body with the same parameters. In addition, its radius is twice as large as calculated based on the modern stellar structure theory. Strangely enough, another unusual feature of the star has helped to provide answers to these riddles. According to spectral analysis of its radiation, the stellar matter of AP Columbae contains an abnormally large amount of lithium. Normally, this element is found in abundance in protostellar clumps, but it burns out completely after the start of a thermonuclear reaction. This means that the star is very young and at the very beginning of its formation, not even in the main sequence phase yet. As a consequence, AP Columbae is unstable and explosive in nature. It is prone to violent outbursts and stellar matter ejections, during which its luminosity may increase by up to 10 times for a short while. Such events would normally threaten exoplanets nearby, stripping off their atmosphere and sterilizing their surface with ultraviolet radiation. As it is, observations show that there are no large space objects within 4.5 astronomical units of this star. In all likelihood, it is too young for the formation of fully fledged planets. Nevertheless, it is a unique cosmic body, very important for understanding early evolutionary stages of stars. As we've seen, not every star has a planetary system, so our next stop is near the orange dwarf Gliese 370, 37 light-years from Earth. In 2011, a single exoplanet was discovered near it, designated Gliese 370b. The object was discovered with the use of the radial velocity method and has a mass of 3 to 4 Earths. According to current understanding of the formation of celestial bodies, the discovered world is most likely a rocky planet, with a radius about 30% larger than the Earth's. Under such conditions, the gravity on its surface may be at least 40% higher than what we're used to. Gliese 370b is located at a distance of 0.26 astronomical units from its parent star and completes an annual rotation in 54.4 Earth days. Thus, the exoplanet is in the habitable zone of its star. If the albedo value of its surface is close to that of the Earth, then the average temperature of the celestial body should be about 25 degrees Celsius, which is a few degrees higher than on our Earth. The fact that an exoplanet is located quite far from its parent star suggests that it is not tidally locked and has its own diurnal cycle. This contributes to an evener distribution of heat over the surface of the celestial body, which as a consequence may create a milder climate. A moderately high gravity should smooth out the planet's terrain, which combined with an abundance of liquid water may cause vast seas to form, both warm and shallow. Such places have traditionally been considered the most comfortable for the genesis and support of life. At the time of its discovery, Gliese 370b was considered one of the most favorable exoplanets for potential biological life. However, more recent research has suggested that conditions on its surface are somewhat less attractive than previously thought. In particular, the atmosphere of the celestial body may be too dense and have a pronounced greenhouse effect. Still, even according to the most pessimistic predictions, the average temperature on the surface of the object does not exceed 78 degrees Celsius, which corresponds to a temperature range of about 30 to 100 degrees Celsius. Given that our planet's climate was about the same during the Archean period, Gliese 370b remains a very promising exoplanet for the search for extraterrestrial life, which means that its exploration must continue. If we stop and look around for a while, we will find that we have already traveled more than 50 light-years away from our solar system. There are over 1,000 stars within its radius, most of them single stars. Others are binary stars or even groups of stars. The most striking example is Castor, a complex and surprising system of as many as 6 components. This stellar system is located 50 light-years away from Earth and is visible to the naked eye as a single source of light. As the second brightest object in the constellation Gemini and the 23rd brightest in the night sky in general, Castor has been known to humans since ancient times. As the system has as many as 6 components, it has a rather complex structure. The 2 brightest of these, Castor A and B, are bluish-white Sirius-like stars, each with a red dwarf companion nearby. The distance between the mass centers of these binaries is about 110 astronomical units, and it takes them 445 years to complete a full orbit. About 600 astronomical units from Castor A and B, there is another compact binary system, consisting of a pair of almost identical red dwarfs. Each has a mass of about 0.6 times that of the Sun and has a surface temperature of about 3,900 Kelvin. The 2 stars are so close together that they take less than 20 hours to complete a rotation. They move around the system's common mass center following a very oblong elliptical orbit with an orbital period of about 14,000 years. So far, no confirmed exoplanets have been found in the Castor system. But if they do exist, they're most likely to be located here, near the faintest component of the system. In 2018, for example, astronomers detected variations in the orbital period of Castor C, which implies there may be a brown dwarf nearby, about 49 times more massive than Jupiter. According to calculations, it is located 14 astronomical units from the parent star and completes a full orbit around it every 54 years. It is possible that, like many red dwarfs, Castor C has rocky exoplanets close by. In this case, the skyline of such a hypothetical object must present a truly incredible spectacle. On one side, a considerable part of it is occupied by 2 crimson stars circling the sky without stopping, while on the other side, the eternal twilight is diffused by the light of a pair of stars, either of them hundreds of times brighter than the Earth's moon. Whether this is actually the case cannot yet be verified at this point. Although the stars we have visited are great distances apart, they are all within a single structure stretching for the total of about 300 light-years. This is called the local bubble and contains not only thousands of stars, but also several large structures, including the local interstellar cloud. The local bubble was formed by successive explosions of several supernovae that occurred between 10 and 15 million years ago. It is a giant cloud of interstellar gas heated to 1 million Kelvin. Because of its high temperature, the gas tends to expand, so its density is about 10 times lower than the galactic average. In addition, the hot ionized hydrogen constantly emits X-rays. Fortunately, the magnetic fields of the Sun and the Earth, as well as the atmosphere of the planet, successfully protect us from the harmful radiation. The local bubble is bordered by other similar formations. For example, slightly away from the direction of the solar system's motion is the so-called Bubble 1, formed by supernova explosions in the vicinity of Antares. This giant cosmic structure has been actively interacting with our bubble for a long time, which has caused the formation of tremendous compactions located at the region at the edge. The center of the neighboring bubble is about 500 light-years from us, and the solar system will reach its margins in a few tens of millions of years. Clouds of scorching hot gas and dopant clusters, giant nebulae and stellar streams. All these majestic cosmic structures add up to a single system called galaxies. In turn, they combine to form galactic filaments, giant streams and walls stretching for billions of light years. This forms the large-scale structure of the universe, with countless different stars and worlds lurking in its depths. Who knows what we're eventually to find among them? Our galaxy counts around 200 billion stars and not less than 1 trillion exoplanets. Each of these celestial bodies is unique and has its own peculiar properties. Among the stars of the Milky Way, there are some supergiants capable of swallowing up entire stellar systems, but also there are absolutely tiny ones, barely glimmering in the boundless abyss of space. Some of them are solitary, while others make pairs and even form complex systems made up of several various objects. Following the immutable laws of gravity, new glittering stellar clusters and majestic associations form in the Milky Way among dark nebulae and bubbles of red-hot hydrogen. If we look at an area of space within the radius of 50 light-years from our Sun, we will observe around 2,000 stars here. We've looked at some of the most notable ones before, such as the fast-going Barnard star, the mysterious Proxima Centauri, the shining Sirius, and the diverse multiple Castor star system. And so it means that today, it's high time to set out much further out there. Having left the solar system far behind, as it were, we will notice that it is in the so-called local bubble. This giant structure is an area of hot, rarefied hydrogen surrounded by a layer of cold cosmic dust. It is believed that it came into existence on several almost simultaneous supernovae, and to date, its diameter is anything bigger than 300 light-years. These structures are called supershells and may even go beyond the galactic disk. Our planet is in a part of the local bubble called the local interstellar cloud. Approximately in 8 million years' time, which is quite soon by space standards, our system will leave it to enter a larger area known as the Loop 1 bubble. This superbubble is located approximately at the center of our galaxy and is as big as ours. It is partially intertwined with the local bubble, and its boundaries are rather blurred, so it is hardly possible to determine the exact distance to it. Currently, this value is estimated in the range of 250 to 300 light-years. The center of this giant cosmic structure is located away from the vector of motion of the solar system and is about 500 light-years from Earth, near a bright star called Antares. One of the unusual and notable stars located near the conventional boundary of the two bubbles is Spica, also known as Alpha Virginis. This star is one of the brightest objects in the night sky of our planet and is easily discernible in it with the naked eye. Calculations show that Spica is about 250 light-years away and is a multiple star consisting of 5 objects. According to observations, 3 of the 5 components are distant stars, and none of them can be seen from Earth without the aid of optical instruments. The smallest of these, known as Spica B and Spica C, are very faint objects at the periphery of the system, and studying them is a bit of a challenge. Spica B is about 6,000 astronomical units away from the common mass center, while Spica C is even further away, at about 14,000 astronomical units. Another component, Spica AC, is very close to the center of the system and completes a full orbit around it approximately every 660 days. It is a blue-white star 4.4 times more massive than our Sun, and the radius of its orbit is about 4 astronomical units. Still, astronomers are mainly interested in a bright binary star, which is actually the one usually called Spica. Both of its components are located very close to each other, so much so that even the best modern telescopes are not able to distinguish them as separate objects. Such stars are called spectroscopic binaries, and the parameters of each star are calculated from periodic changes in the overall spectrum. This is how astronomers became aware that the main object of this system, referred to as Spica AA, is a large blue-white star. It is about 11.4 times more massive than our star, and its radius is about 7.5 times that of the Sun. At the same time, its surface temperature is over 25,000 Kelvin, which makes it more than 20,000 times brighter than the Sun. Thus, it is Spica AA that makes the main contribution to the total luminosity of the entire system. Its closest companion, Spica AB, is noticeably inferior in terms of luminosity. It is only 2,254 times brighter than our star. Its mass is 7.2 solar masses, and its radius is approximately 3.7 times bigger than that of our Sun. It is also known that Spica AB is a very hot star, with a surface temperature of 20,900 Kelvin, or about 20,600 degrees Celsius. According to calculations, the distance between the components is only 0.12 astronomical units. That is 4 times shorter than the distance between Mercury and the Sun. Such proximity leads to the fact that powerful gravity deforms them and gives them an elongated, elliptical shape. Spica's total spectrum has a very complex structure. Firstly, observations show that each of the components is a so-called beta Cephei type variable. The processes occurring in their interior cause the surface of such stars to constantly pulsate, with powerful shock waves running across the surface as a result. These pulsations are made up of dozens of clear rhythms, but it may not be easy to distinguish them. Secondly, each of these objects has its own rotational speed. Usually close twin systems synchronize their motion due to tidal forces. But in the case of Spica, either star spins with its own rhythm. Most likely, the lack of synchronization is accounted for by the small age of this binary star. According to calculations, it was born only 12.5 million years ago. However, we cannot completely dismiss the idea that the components of Spica were born in different places and later came to be attracted to each other. If current theories of stellar evolution are correct, then the main component of the system is no longer a main sequence star and is close to exhausting its thermonuclear fuel. It will soon begin to expand and cool down, which may lead to the flow of stellar matter to the second component. This process is called accretion, and it has a significant effect on both stars involved. Similarly, the smaller component increases in mass, which causes it to gradually become brighter, but it ends its life cycle more quickly. It is thought that within a few million years, this process will lead to a Type II supernova, and Spica is the closest candidate for this tremendous and rare event. Eventually, the internal energy of the larger of the stars will become insufficient to resist the inexorable gravitational collapse, at which point it will shrink and then explode, scattering the outer layers around. In all likelihood, the explosion will break the bond between the two stars, setting one of them free. In the end, instead of the bright binary star, there will remain just a tiny and very dense neutron star, virtually invisible in the optical range. Meanwhile, Loop 1 contains many other bright stars, including the giant Scorpius-Centaurus association, which may count more than 2,000 stars, according to the latest estimation. According to the currently accepted hypothesis, it is here that several large stars went supernova almost simultaneously, about 15 million years ago. It is this event that caused the formation of a giant bubble of highly ionized hydrogen, known to us as Loop 1. Calculations show that the temperature of interstellar gas in this part of our galaxy is over 1 million Kelvin, but its density is very low. Only about 50,000 atoms can be found in a cubic meter of space. This is about 10 times less than the average for the Milky Way and 100–200 times less than the near-Earth space. That is the space familiar to us, in which almost all satellites and orbital stations are located. Such a high temperature causes the gas inside the bubble to constantly create a very weak but high-frequency radiation background. Fortunately, potential life within it is not threatened, because the stellar wind of even the smallest star is able to deflect this radiation. If the radiation does reach the hypothetical exoplanet, the upper layers of the planet's atmosphere are also able to offer protection, absorbing the radiation successfully. In fact, the Scorpius-Centaurus stellar association extends far beyond the Loop 1 superbubble. For example, a massive, dense and dark nebula known as the Coal-Sack Nebula is part of it. From Earth, it can be made out as an impenetrable black spot in the constellation of the Southern Cross. It is particularly noticeable because it covers part of the Milky Way. This structure is adjacent to Loop 1 as its natural boundary and is a giant dust cloud. The Coal-Sack is located about 600 light-years away, and its diameter is estimated to be about 30–35 light-years. In Earth's night sky, it occupies 24.2 square degrees, which is 138 times the area of the full moon, or about a third of the total surface area of the Southern Cross. The nebula itself has almost no stars visible to the naked eye, but with the help of powerful telescopes, we can see some bright stars behind it. Their light is largely scattered as they pass through the dust cloud, so a lot of the information about the objects behind the Coal-Sack gets irretrievably lost. Calculations show that in a few million years, due to the rotation of the galaxy, this nebula will be illuminated by starlight and is likely to offer an incredibly beautiful sight, a giant multicolored spot in the night sky. And after a long time, after its own gravity compresses it sufficiently to trigger the formation of young stars, the Coal-Sack will transform into a sparkling open cluster. As we continue our flight through the Scorpius-Centaurus association, we notice that most of its stars are located in the relatively clean and empty space of the giant bubble. At its fringes, however, a very different environment surrounds them. Here, cosmic dust accumulates, displaced by stellar winds, echoes of supernovae, and glowing, expanding hydrogen. It is here, 440 light-years from Earth, that a large, bright and young star known as Zeta Ophiuchi is making its way through the blurred cosmic nebula. This celestial body is a blue giant, about 20 times more massive than our Sun. Studies of its spectrum show that its average surface temperature is over 35,000 Kelvin, which means that its radiation peaks in the far ultraviolet range. Analyses of the object's motion show that it was once part of the Scorpius-Centaurus association, but as a result of some event, left it and is now rapidly moving away. The cosmic dust surrounding the star absorbs and scatters much of the light it emits. Were it not for this phenomenon, Zeta Ophiuchi could be among the brightest stars in the night sky of the Earth. Due to its impressive size and temperature, it emits 74,000 times more energy than the Sun. Thanks to this, even now the star is not only clearly visible in the night sky, but is among the 100 brightest objects there. The movement of Zeta Ophiuchi, in combination with the most powerful stellar wind, forms a luminous shockwave that looks like a hemisphere, and it faces the direction of its flight. By the brightness of this cosmic phenomenon, we can determine the activity of the stellar wind. Calculations show that the star loses about 1.1 times 10 to the power of -7 solar masses per year. In other words, every 9 million years, the mass of one sun is ejected into the surrounding space. Observations of the spectrum of Zeta Ophiuchi show that its surface is intensely pulsating under the influence of shock waves generated by processes in the interior of the celestial body. In addition, this star is rotating very fast. It completes a full rotation in about 1 day. And the speed of matter at the equator of the celestial body reaches 400 kilometers per second. For this reason, the shape of Zeta Ophiuchi is far from spherical. While its equatorial radius is more than 9 times larger than that of the Sun, the polar radius barely reaches 7.5. The temperature of the star is also unevenly distributed, from 30,700 Kelvin at the equator to 39,000 Kelvin at the poles. In addition, calculations show that because of the ultra-fast rotation, the giant star is on the verge of collapse. If it rotated even a little faster, the force of inertia would tear it apart. Despite its age of 3 million years, which is young by cosmic standards, Zeta Ophiuchi has already passed the halfway point of its life, and will soon turn into a red giant before going supernova, leaving behind a neutron star. Just a little away from this giant star is an object that is radically opposite to it in terms of its properties. The distance from it to Earth is known only approximately, and according to calculations, is about 400 light-years. This celestial body is not visible from our planet with the naked eye, and therefore does not have a beautiful name. Instead, it is known under a bland, tongue-twisting index, which is right here on the screen. This space object is a neutron star, a remnant of a burned-out star left after a supernova. Although its mass is greater than that of most stars, its size is comparable to that of a small asteroid. For this reason, this celestial body cannot be seen even in the most advanced optical telescopes. Still, it emits powerful X-ray pulses that can be detected at a distance of thousands of light-years. For a long time, astronomers did not know about the existence of such cosmic objects. Only with the advent of X-ray telescopes, which see the cosmos in a spectrum inaccessible to humans, were we able to detect them. In addition, neutron stars are very rare in the universe, about 1,000 times rarer than ordinary stars. Given all these facts, it is not surprising that the object we're talking about was discovered relatively late, in the 1990s to be more exact, and is still the closest representative of its class to Earth. Obviously, a specimen located that close provoked great interest among astronomers, as well as a desire to comprehensively study such an unusual space object. The first measurements showed an extremely high temperature of this body's surface, so for a long time it was considered a candidate for the role of a hypothetical quark star. But later, with the data significantly refined, the object turned out to be an ordinary neutron star, although very rare, very young and hot. This celestial body is believed to have formed after a supernova explosion about 1 million years ago. According to the latest data, its radius is about 12 kilometers, and its surface temperature is more than 250,000 Kelvin. This value seems incredible, because the absolute majority of neutron stars known to us have temperatures of only a few thousand Kelvin, which is comparable to ordinary stars. However, calculations confirmed by observations show that at the moment of their birth, these objects can be as hot as several million Kelvin. Subsequently, they cool down very quickly, so it's a great deal of luck to find such a hot neutron star located at a relatively short distance from Earth. By studying such objects, astronomers gain valuable insights into the evolution of these mysterious celestial bodies. Despite advanced theoretical models, many aspects of neutron star physics remain largely understudied. For example, according to calculations, the gravitational field of supercompact and supermassive objects should so strongly distort the surrounding space that their description requires adjusting the usual laws of physics. In the neighborhood of neutron stars, this distortion combines with extra strong magnetic fields to produce physical phenomena impossible in most of the universe. It was here, near the closest neutron star, that one such phenomenon, known as vacuum birefringence or the Euler-Heisenberg effect, was discovered. The phenomenon is this: when passing through a strong magnetic field in a region of high gravity, light deviates from its linear motion, splitting into many rays with different planes of polarization. It is noteworthy that this effect was first predicted theoretically, then reproduced in laboratories on Earth, and only as recently as in 2016 was it detected in nature, just near this neutron star. Currently, it remains the only object that reliably demonstrates this fantastic phenomenon, although in recent years there have been indirect signs of its detection in other similar celestial bodies. Of course, research of this amazing cosmic object continues because there is still a lot we don't know about the structure and evolution of neutron stars. Meanwhile, almost in the opposite direction of the Scorpius-Centaurus association and the superbubble surrounding it, there are two magnificent star clusters in the direction of the well-known constellation Taurus. The closest of these is the Hyades, about 150 light-years away. This cosmic structure is an open star cluster, about 650 million years old. Incidentally, it is half destroyed by the gravity of the Milky Way. At the time of its formation, its total mass was over 1,200 solar masses, but since then most of the stars have left the cluster. At present, the central part of the Hyades is a very dense cluster of closely spaced stars with a diameter of about 10 light-years. Around this core, there is a tidal zone with a radius of about 30 light-years, where a considerable number of stars is concentrated, with a total mass of about 250 solar masses. Also, from the main part of the Hyades, there extend two very long tails. Observations reveal their length to exceed 2,500 light-years. It is believed that the cause of their formation was the gravitational impact of the massive core of our galaxy on the cluster. One of these stellar streams is directed towards the center of the Milky Way, and the second one in the opposite direction, to the edge of the galactic disk. Although the Hyades have been known to humans since ancient times, these structures were discovered for certain only in 2018. This was possible thanks to analyzing the proper motion of a considerable number of stars, which were not previously thought to be part of the cluster. In total, there are more than 700 stars in the Hyades, with a combined mass of 435 solar masses. Among these stars, there are no large ones. Such objects would have completed their evolution and transformed into white dwarfs by now. Currently, the cluster is known to contain 4 red giants, gradually completing their life cycle, and 9 white dwarfs, which have already exhausted the reserves of thermonuclear fuel. In addition, 27 brown dwarfs have been discovered, peculiar objects too small to be stars and too large to be considered planets. More than a dozen stars can be seen in the cluster with the naked eye, and one of the most massive, bright and interesting members of the Hyades is Epsilon Tauri, also traditionally known as Ein, or the Northern Eye. This star is located about 150 light-years from Earth and is visible in the night sky without the aid of a telescope. It has already passed the main sequence stage and evolved into an orange giant with a helium core surrounded by a rarefied envelope, not very hot by stellar standards. At the moment, Ein has a mass 2.7 times that of the Sun and a radius 12.5 times that of the Sun. Its surface temperature is lower than that of the Sun and is about 4,900 Kelvin, or a little over 4,600 degrees Celsius. Due to this body's impressive size, its luminosity is 80 times that of our parent star. At the moment, Epsilon Tauri is one of the largest stars near which exoplanets have been discovered. The celestial body named Amaterasu was discovered in 2007 and was the first exoplanet discovered within an open star cluster. The object moves along a moderately elongated orbit around its parent star, completing it within roughly 645 days. The average distance between the planet and the center of the system is about 1.9 astronomical units, but due to the elongated trajectory, this can vary significantly with time. In addition, the proximity of other massive stars can perturb the motion of the celestial body. For example, in 2023, oscillatory deviations in the motion of this exoplanet were recorded, which is something that may be caused by the tidal influence of the parent star, or else the influence of neighboring stars. Amaterasu's mass is 7.6 times that of Jupiter, and its radius is 18% larger. Due to the intense brightness of the central star, the average calculated temperature of Amaterasu is quite high. It is 541 Kelvin, or 268 degrees Celsius. Thus, this celestial body may be classified as a hot superjupiter. It is also highly probable that there may be large satellites located near it, close to Mars or even Earth in size. However, the chance of these hypothetical celestial bodies being potentially habitable is small. Unfortunately, this system is at the final stage of its evolution, as the central star has almost exhausted its stellar fuel reserves. Soon it will shed its outer shells and transform into a white dwarf, with the surrounding planets either getting destroyed during this process or frozen as a result. In addition, after about 30 million years, the Hyades will lose gravitational binding and disintegrate completely. The stars that formed part of this constellation will scatter across the galaxy, and only indirect signs will indicate their common origin. If we travel deeper into the cosmic abyss, we will soon reach another major star cluster. It's about 445 light-years from Earth, and it's called the Pleiades. According to calculations, this open star cluster contains about 3,000 objects, with a total mass of more than 800 solar masses. However, to date, only 1,200 stars are catalogued, while the rest remain undiscovered. Among other things, about a quarter of the objects in the cluster are thought to be brown dwarfs, too dim and cold to be seen among their brighter neighbors. Calculations show that this cluster is 115 million years old, which is fairly old for such structures. It is estimated that 2/3 of the stars that once made it up have already left the cluster. The Pleiades were originally comparable in brightness and size to the Orion Nebula. Modeling shows that in 500 million years, there will be only a few hundred stars, most of them small and dim, such as red and brown dwarfs. And when the age of the cluster reaches 1 billion years, it will retain only a few dozen objects. If the Pleiades approach a massive object during that time, such as a gas and dust cloud or a globular cluster, the disintegration will run its course even faster. The brightest star in the cluster is Alcyone, also known as Eta Tauri. This object is located 440 light-years away from Earth and is a multiple star made up of 4 components. However, 3 of them are not visible to the naked eye. The main contributor to the luminosity of this system is the blue-white giant Alcyone A, which has a mass of about 6 solar masses. According to calculations, its radius is anything between 8.5 to 10 times that of our star. At the same time, analysis of the radiation of this star shows that it rotates around its own axis extremely fast. The speed of movement of the outer layers at the equator of the star reaches 215 kilometers per second, which is about 100 times more than the Sun. As a consequence, Alcyone A is highly deformed and has the shape of a flattened ellipsoid. The force of inertia, combined with a powerful stellar wind, causes particles to leave the surface of the object and collect in a ring-shaped hot nebula around its equator. The average surface temperature of the star is 12,250 Kelvin, but it is lower at the equator and much higher at the poles. This causes the star's luminosity to be also unevenly distributed across its disk. On average, Alcyone A is more than 2,000 times brighter than the Sun. According to modern models of stellar evolution, the age of this star is estimated at about 70 million years. This is much lower than the average age of the Pleiades, which is about 130 million years. This could mean that Alcyone A was captured by the cluster after its formation. Other components of the system are at a noticeably far distance from its center, 10,000 astronomical units or more. The stars, known as Alcyone B and C, are blue-white main sequence stars. The former can even be seen with the simplest optical devices, such as the most common binoculars. Alcyone C is remarkable for its luminosity, which changes with a surprisingly clear periodicity. During a period of 1 hour and 8 minutes, the luminosity of Alcyone C gradually increases by about 5%, and then slowly returns to its previous value. This phenomenon is associated with processes running in the star's interior, which generate periodic shock waves, traveling along the surface. The fourth component of the system is Alcyone D, a white and yellow star slightly larger and more massive than the Sun. Speaking about the planetary systems of these stars, their search has not yet been successful. Perhaps they are in orbits inconvenient for observation, or were subjected to destructive tidal influence of nearby massive stars. Either way, the high activity of the parent stars would very likely make life on them impossible. A glance over the region around the solar system, with a radius of a few hundred light-years, will show that it contains not only a wide variety of stars, but also giant clouds of dark dust, bubbles of red-hot hydrogen, and other amazing objects. Further away, it is easy to see that this area is only a small patch of space on the edge of the tremendous galactic arm of Orion. Against the background of the entire Milky Way, it is almost invisible. Meanwhile, our galaxy itself is just a shining grain of sand among the gigantic clusters and bottomless voids that form the large-scale structure of the universe. It is difficult for the human mind to grasp and visualize this infinite variety of the cosmos, and even more difficult to accept that we may be seeing only a tiny part of it. As a rule, it's potentially habitable planets with favorable conditions and a moderate climate that especially catch one's attention among the great diversity of other worlds out there, or else, on the contrary, extremely dangerous objects stand out among others. Still, there is yet a third category. It's anomalous celestial objects manifesting unusual behavior which is barely scientifically accountable. Objects like that challenge our knowledge and deserve special attention. This is exactly the kind of world we'll be looking at now. The year 2009. The environs of the Kepler 413 system. An unknown object passes between our planet and a distant star, briefly reducing its luminosity. astronomers take this event to be a standard exoplanet transit and announce the discovery of a new celestial body. High-precision calculations even make it possible to determine its parameters. The planet turns out to be a cool giant, with a mass of about 25 times that of the Earth and a radius of about 40% that of Jupiter. However, 180 days later, another expected transit never occurred. The planet, so clearly visible in the old data, seemed to have vanished without a trace. A dark spot in the photosphere of the star, or a giant dust cloud moving in its vicinity, would have accounted for the mysterious phenomenon. But these hypotheses were dispelled when 800 days later the mysterious object reappeared just as suddenly as it had vanished. The hypothetical planet eclipsed the disk of its parent star 5 times before disappearing again. Still, the key to the riddle had been found. It turned out that Kepler 413b has a highly unusual orbit. The celestial body is located near a binary star and is 0.36 astronomical units from the system's common mass center. Its trajectory is constantly affected by gravitational perturbations, and the change in gravitation of 2 nearby stars shifts the orbital plane considerably, causing cyclic oscillations. When the deviation reaches its maximum, the object leaves the line of vision and then returns to it. Calculations show that Kepler 413b's orbit oscillates with a periodicity of about 11 years, deviating 2.5 degrees in each direction from its average value. The planet's own axis of rotation also changes its position significantly, with a maximum angle of inclination of up to 30 degrees. Combined with a notable eccentricity of the orbit and its periodic shift, the climatic conditions on the surface change in a bizarre way. The region that receives the most light from the parent star is constantly shifting from the equator to the poles and back, which leads to dramatic variations in temperature. It is likely that this process generates huge planetary-scale hurricanes, which can be larger than the Great Red Spot of Jupiter. Air currents can carry ice clouds at several kilometers per second, gradually becoming unstable and dispersing. Meanwhile, the collision and deformation of vortices is capable of causing tremendous atmospheric emissions that have the power to overcome the planet's gravity and reach outer space. According to calculations, they will hang a while up there before gravitational forces pull them back down. All these incredible phenomena make the planet a rather harsh place. However, it may seem like a tranquil, serene island in comparison to the following world. "190 light-years from Earth. The environs of the HD 10606 system." This yellow dwarf, surprisingly similar in parameters to the Sun, is orbited by a planet with a highly variable climate. It whizzes towards its parent star as rapidly as a giant comet, burning itself in the hot rays of its corona, only to retreat to the periphery of the system. The object is a gas giant, with a mass 4 times that of Jupiter, and a radius slightly different from that of Jupiter. At the furthest point in its orbit, the planet is 0.88 astronomical units away from the parent star, and receives about as much heat from it as the Earth does from the Sun. It has been suggested that this is when clouds consisting of water vapor droplets, ice crystals, or even microparticles of quartz may condense in its atmosphere, and temperatures on the surface of the hypothetical satellites of the gas giant could be comparable to those on Earth. But as the planet gets closer to the star, conditions on it change very quickly. Within 55 days, the distance between them shrinks by a factor of nearly 30, and the energy flux from the star increases by a factor of 800. Observations show that at the lowest point in its orbit, the exoplanet's temperature roughly doubles within a matter of just 6 hours, from 500 to 1200 degrees Celsius. Such drastic changes result in violent hurricanes, which can reach speeds of up to 5 kilometers per second. By absorbing an incredible amount of heat, the atmosphere of the gas giant expands so fast that it produces shock waves capable of sweeping across the entire planet multiple times. Water vapor is broken down into oxygen and hydrogen by the temperature, and quartz crystals evaporate without a trace, only to recondense into gigantic sand clouds later. In all likelihood, HD 80606b is the only planet in its system. The gravity of another nearby star has not only warped its orbit, but has also wreaked havoc on the protoplanetary disk. So the chances of encountering other large objects nearby are rather slim. However, destabilization of a planetary system due to the interaction of celestial bodies is not uncommon. (1,530 light-years from Earth), the environs of the Kepler-36 system. The central object in this system is a yellow subgiant. Its mass is comparable to that of the Sun, and its radius is 62% larger than that of our star. There are two planets rapidly orbiting the star, a rocky super-Earth and a hot mini-Neptune. Every 97 days, they mutually approach at a critical distance of only 1.9 million kilometers, about 20 times less than the minimum distance between the Earth and Venus. At such moments, their mutual attraction causes global cataclysms, but after a few days, the celestial bodies diverge again until the next resonance. According to calculations, the gravitational interaction between the planets at the point of closest approach is about 13 times higher than that between the Earth and the Moon. In particular, this effect should be seen on the surface of the rocky planet. Under the influence of titanic forces, its crust may crack and shift, causing earthquakes of incredible power. The resulting chasms may be hundreds of kilometers long and cause multiple eruptions of gigantic volcanoes. It is likely that some regions of the planet do not cool down in the short period of relative tranquility, creating seas of eternally bubbling, red-hot magma. The reasons for the formation of such an unusual system are still debatable. We now know that the super-Earth, dubbed Kepler-36b, is 0.12 astronomical units away from its parent star, and it takes 14 days to complete a full orbit around it. The super-Earth's mass is 3.8 times that of the Earth, and its radius is 1.5 times that of our planet. The object has been calculated to have a temperature of 980 Kelvin, or just over 700 degrees Celsius, and an average density of about 30% higher than that of the Earth. The data suggests that the celestial body could be a Chthonian planet, the core of a gas giant that has lost its atmosphere. Such objects contain many heavy metals like iron and lead, as well as sulfur and silicon compounds. It is likely that the light elements that once made up the thick, dense shell of the celestial body may have been blown into space by stellar wind. Nor should we forget the second planet's gravitational pull, which could potentially have contributed to this process. The object is called Kepler-36c and is likely to fall into the class of hot mini-Neptunes. The celestial body moves in a nearly circular orbit with a radius of 0.13 astronomical units and completes it every 16 days. Its mass is 7 times that of our planet, and its radius is 3.7 times that of the Earth. Because of its proximity to the star, the temperature of the object is also very high, 928 Kelvin, or 655 degrees Celsius. This celestial body should be surrounded by a thick, multi-layered atmosphere consisting mainly of nitrogen, hydrogen and helium. Deeper down, the pressure inside the gas shell increases, and it gradually turns into an ocean of supercritical fluid surrounding the solid core. Meanwhile, under certain conditions, truly fantastic phenomena are also possible. For example, the gravity of a more massive planet can potentially capture satellites from its smaller companion, while tidal forces may destroy them to form vast asteroid streams. In addition, the mutual gravitational pull of the two planets distorts their orbits, altering eccentricity and other parameters. Because of this, the entire system behaves chaotically and unpredictably, and its evolution cannot be predicted over any extended period. Modeling shows a 91% probability that the two planets will collide with each other over the next 70 million years, producing hundreds of thousands of pieces of debris which will disperse throughout the planetary system, thereby creating a still greater chaos within it. Such tremendous cataclysms may have occurred more than once in the following system. 434 light-years from Earth. A surprising object, informally called Super Saturn, is located 4 astronomical units away from a young Sun-like star. It is a brown dwarf, or a large gas giant, 20 times as heavy as Jupiter. Observations show it to be a young planet, about 15 to 16 million years old, which is still forming. Most of its atmosphere consists of hydrogen and helium, with a massive metallic core in its depths. This object is spun by a system of rings, like Saturn's but much larger. The transit method revealed at least 37 distinct rings, with the largest one's outer radius measuring about 0.6 astronomical units. This is comparable to the size of Venus's orbit, and about 640 times the radius of Saturn's rings. According to calculations, the total mass of the circumplanetary disk is bigger than the mass of the Earth, and its behavior manifests signs of randomness. Mathematical modeling shows that such structures are not stable and gradually disintegrate. Some of the objects making them up lose velocity and fall to the central planet, while others, on the contrary, accelerate and leave the disk forever. However, this process is greatly extended in time and may take several 100 million years. Also, a large rupture with a radius of about 0.4 astronomical units was detected in the system of rings, which is considered indirect evidence of the existence of an exosatellite in this region, about 80% the mass of the Earth. According to current understanding of the physics of space objects, it is a kind of object capable of clearing its orbit of small debris, forming a wide rupture in the ring structure. In addition, observations suggest the presence of at least 2 more celestial bodies, with a mass of each of about 30% that of the Earth, and located at a distance of about 0.25 astronomical units from the center of the brown dwarf. Just like it is the case with the large planets known to us, it can be assumed that a total of several hundred exosatellites, including rather massive ones, may be located within the gravitational influence of the central object. A simulation of such a system, including radiation from a parent star, heat flow from a giant planet, and tidal influences, shows that the temperature of the celestial bodies making it up could approach comfortable values. One can only imagine how enchanting the night sky would be from the surface of such an exosatellite. At this distance, the brown dwarf occupies 70 times as much space in the sky as the full moon, and its soft glow can dispel the darkness and turn the night into a misty twilight. Instead of the star-spangled canopy, the planet's sky is crisscrossed by vast swathes of light from horizon to horizon. At the same time, the tidal forces of a nearby massive body could provoke multiple eruptions on the satellite's surface, and its hypothetical ocean could slam the land with giant waves. The width of a tidal zone under such conditions could reach hundreds of kilometers, making it a unique climatic zone, something like a cross between land and the ocean floor. Still, it should be mentioned that such structures tend to be unstable and change their appearance quite quickly beyond recognition. It is difficult to say how much longer we'll be able to admire the giant rings and what they will look like in millions of years. It can hardly be disputed that life is one of the most amazing, complex and mysterious phenomena in the universe. Despite the fact that we've been studying it for thousands of years, many important questions about it still remain unanswered, and the greatest among them is how widespread is biological life beyond our planet. At this point, we cannot yet say with a satisfying degree of certainty whether the Earth's biosphere is a unique phenomenon or whether it has emerged as a natural and logical result of continuous evolution. It is hardly surprising that the search for life beyond Earth is one of the most important fields in science. And in order to identify the most promising celestial bodies in this respect, the so-called Earth Similarity Index, or ESI, is used. It is based on two main parameters: the level of gravity on the surface of a celestial body and its equilibrium temperature. It is these parameters, according to scientists, that determine how much the other world can be similar to Earth and how favorable the conditions on its surface are for hypothetical life. The undeniable advantage of the ESI is its simplicity, because when an exoplanet is discovered, you can usually determine its approximate orbit, mass and size, and this information is just enough to calculate the basic parameters of the index. However, for all its appeal, it does not take into account many factors critical for sustaining life. Therefore, we will allow ourselves to be as presumptuous as to formulate our own evaluation system, taking the ESI as the basis and supplementing it with several important parameters. The activity of the parent star can be singled out as one of them. It is known that frequent flares and stellar matter ejections, characteristic of red dwarfs, can adversely affect the stability of the atmosphere and radiation background of the nearest exoplanets. Nevertheless, red dwarfs are considered more favorable than large stars, like Sirius or Vega, because the lifespan of giant stars is too short and the radiation is too destructive, leaving no chance for potential life to develop. The most favorable ones are orange and yellow dwarfs, including our Sun. The probability of tidal locking is another significant factor to be reckoned with. This probability depends on the distance between an exoplanet and its star. Celestial bodies located too close to their stars permanently face them with one side only. As a consequence, there is a large temperature difference between their day and night hemispheres. Too great a distance from the source of heat and light puts the planet outside the habitable zone, which drastically reduces the chances of the genesis of life. It is also necessary to consider the type and chemical composition of a given exoplanet, because in order to develop, hypothetical life requires a certain set of chemical elements, in combination with characteristic relief. Such conditions can be seen on rocky, terrestrial-type planets, or super-Earths. Mini-Neptunes, meanwhile, do not have solid surfaces, and ocean planets are deficient in many elements. Thus, the set of parameters we have specified allows us to comprehensively assess how favorable the conditions on a given exoplanet are for hypothetical life. For example, in a scheme like this, the Earth looks extremely attractive against these parameters, being the natural benchmark for other objects. At the same time, Mars, although it has the highest similarity index to our planet in the entire solar system, has a number of obvious disadvantages. It is too cold, too low mass, and demonstrates a significant water deficit. Venus, on the other hand, despite appearing very similar to Earth on the face of it, is too hot because of the strong greenhouse effect. And although most of its parameters are in the green zone, the extremely high temperature is a critical disadvantage of the planet, effectively cancelling out all its advantages. Thus, there are no planets within the solar system sufficiently similar to Earth to be considered favorable for life. However, Beyond its boundaries, more than 5,000 other worlds orbiting distant stars have already been discovered, and in many respects, some of them can be considered similar to our planet. One of these objects, closest to us, is an exoplanet known as Gliese 1002b. It is located just 15.2 light-years from our planet. It was discovered in 2022 using the radial velocity method. This method is effective for finding relatively close exoplanets and involves capturing subtle fluctuations of the parent star caused by the movement of space objects around it. The exoplanet is located near a small and dim red dwarf known as Gliese 1002. Its radius is only 14% that of the Sun, and its mass is 8 times smaller than that of our star. Given that Gliese 1002 has a surface temperature of just 3000 Kelvin, or about 2730 degrees Celsius, it is not surprising that its luminosity is extremely weak. It's about 700 times weaker than the Sun's. Observations also show that the object is quite serene, which is unusual for stars of this class. Due to the low luminosity of this red dwarf, its habitable zone has an extremely small radius and width. However, the object Gliese 1002b is located near its outer edge and can be considered potentially habitable. According to observations, this celestial body completes a full orbit around the center of its system roughly every 10 Earth days. Consequently, the average radius of its orbit is clearly very small and is about 0.046 astronomical units. It is assumed that because of the extreme proximity to the parent star, the exoplanet is likely to be tidally locked, facing it with one side at all times. Calculations show that the celestial body receives 1.5 times less energy from its star than Earth does from the Sun, and its average surface temperature could be approximately 230 Kelvin or 43 degrees Celsius below zero. Incidentally, it is slightly warmer than Mars. Given tidal locking and a possible greenhouse effect, this means that liquid water could be found on the exoplanet's surface, and thus there may be conditions for sustaining life. At least some terrestrial organisms are able to survive in such conditions. Calculations also show that the mass of Gliese 1002b is 8% greater than that of our planet, and the radius exceeds the Earth's radius by only 3%. Using the data, it is not difficult to determine the acceleration of freefall on the surface of the celestial body. It practically does not differ from the value we're used to. Thus, the combination of all known factors suggests that Gliese 1002b is a rocky planet, most of which is covered with ice. Due to its size, which is very near to that of the Earth, it has a rather high ESI of 0.86, and in our scheme this object would look like this. At the same time, modeling of the planet's climate shows that its illuminated hemisphere can receive enough energy to support an ocean of liquid water, with archipelagos of islands or even fully fledged continents. Also, tidal deformations caused by the nearby star warm up the planet's interior, so the existence of an ocean hidden under the ice, even on its night side, shouldn't be ruled out. Incidentally, Gliese 1002b is not the only planet in the system. It was discovered alongside another object dubbed Gliese 1002c, which is located a little further away, namely at a distance of 0.074 astronomical units from the center. A full annual rotation takes this exoplanet 21 days, and its mass exceeds the Earth's by about 36%. The object receives 4 times less energy from the parent star than our planet does from the Sun, so the temperature on its surface is quite low, just about 182 Kelvin or 91 degrees Celsius below zero. If we use the previously developed scheme, then this exoplanet will look like this. It can be assumed that the conditions on the surface of Gliese 1002c are close to those observed on the satellites of Jupiter or Saturn. Increased volcanic activity caused by the planet's high mass could lead to the formation of a hidden ocean, with warm and salty water rich in many chemical compounds. Hypothetically, life could also develop in such conditions, possibly in highly unusual and unexpected forms. Of course, among the great variety of known exoplanets, much warmer and more favorable worlds can be found. Such, for example, is the planet K2-72e, located 217 light-years away. It orbits a small red dwarf, about 4 times less massive than our star. Its radius is 0.33 of the solar radius, and its temperature is relatively low, reaching 3,360 Kelvin or about 3,100 degrees Celsius. Observations made by the Kepler orbiting telescope showed that the exoplanet crosses the disk of the parent star every 24 days. This means that the radius of its orbit is very small and is about 0.1 astronomical units, which implies that the celestial body is located within the habitable zone and can be considered potentially favorable for harboring life. According to the received data, it is also suggested that K2-72e may be tidally locked or in orbital resonance like Mercury. Despite the star's low luminosity, the exoplanet receives 11% more energy than Earth does from the Sun. Assuming that the atmosphere of K2-72e is similar to Earth's, the average temperature on its surface should be about 295 Kelvin or 22 degrees Celsius above zero, which is slightly warmer than on our planet. At the same time, it is worth remembering that if the celestial body is tidally locked, there is a high probability of extreme temperature variations between the day and night hemispheres. In addition to this, it must be taken into account that its parent star, like most other red dwarfs, is erratic and is often observed to flare up and emit great amounts of stellar matter, which can be detrimental to the atmosphere and surface of nearby space objects. Calculations show that K2-72e is 29% larger in diameter than the Earth and is about 2.2 times more massive. Knowing this, we can calculate the level of gravity on the surface of the celestial body. It is about 32% higher than we're used to. Thus, with all the known data taken into account, we can assume that this exoplanet is more likely than not a rocky super-Earth, where liquid water and a dense atmosphere can be found. Its Earth similarity index is quite high and is 0.87, and in our scheme this object will look as follows. Planets of this type are expected to have a wide variety of chemical elements, and their relief should be smooth and favorable for the origin of life. Undoubtedly, the frequent flares of a nearby star pose a tangible threat to the atmosphere, but a powerful magnetic field will hypothetically deflect stellar wind particles, and the oceans will protect their inhabitants from this destructive radiation. In this case, we can assume that on K2-72e, it is possible to observe incredible auroras, by far more impressive ones than on our planet. As for the hypothetical biosphere that could develop on such a planet, it would likely be markedly different from Earth's. A different spectrum of incident light might force local plants to use alternative substances for photosynthesis, so their leaves would likely be purple or reddish in color. In addition, excessive radiation hazards may be an obstacle for life forms to venture on land. Alternatively, it may lead to the evolutionary formation of defense adaptations, such as thick skin or specific cellular structures. Similar features are known to manifest themselves in some terrestrial organisms, such as tardigrades, archaea, and some fungi. Meanwhile, in addition to this planet, so attractive in many respects, 3 other planets have been discovered in the system. Two of them, dubbed K2-72b and K2-72c, are located very close to the parent star and are slightly larger than our Earth. It is assumed that due to the emissions and stellar wind of the nearby star, they are devoid of any atmosphere and are similar to Mercury. The third planet, K2-72d, is estimated to be comparable in size to Earth, and its orbit has a radius of about 0.08 astronomical units. It completes a full orbit around the center of the system approximately every 15 days and is located near the inner edge of the habitable zone. Because of its high temperature, conditions on its surface are likely to be close to conditions on Venus, and the probability of the genesis of life is extremely low. In any case, research on this system is still going on, which means we have much to learn about it in the future. Incidentally, all the objects we have looked at here are similar in size to the Earth. However, life is known to be able to adapt to a wide variety of conditions, including high gravity, which is inevitable on massive planets. If we travel about 1,800 light-years away from the solar system, we can find a yellow dwarf with parameters very similar to those of our Sun. It's called Kepler 452, and it's a main sequence star, just 3.7% more massive and 11% larger than the Sun. In 2015, an extremely remarkable exoplanet named Kepler 452b was discovered near this star using the transit method. High-precision measurements allowed us to calculate that it's located at a distance of 1.04 astronomical units from the center of the system and completes a full annual rotation every 385 days. This location renders the probability of tidal locking of the celestial body extremely low, which is undoubtedly a favorable factor. According to the available data, the object Kepler 452b is about 5 times more massive than our planet, and its radius is about 1.5 times bigger than Earth's. This means that the acceleration of freefall on the surface of the celestial body is 2.2 times higher than we're used to. Such a high level of gravity likely helps the planet retain a dense atmosphere and also smooths out its relief, which could lead to the formation of numerous shallow and warm seas. Such conditions are thought to be the most favorable for the potential origin of life, but gravity this high would be extremely uncomfortable for humans. It is also known that Kepler 452b receives 10% more energy from its parent star than Earth does from the Sun and is in its habitable zone. Calculations show that the average surface temperature of the object is about 300 Kelvin or 27 degrees Celsius above zero, which is 11 degrees more than on our planet. This means that the climate of Kepler 452b may be close to that of the Earth's Mesozoic. However, with a certain composition of the atmosphere, this temperature may be dangerous and may lead to the acceleration of the irreversible greenhouse effect to the point of complete vaporization of the oceans. According to some hypotheses, it was a process of this kind that radically changed Venus several billion years ago. With all the known factors combined, we can assume that Kepler 452b is most likely a rocky super-Earth, rich in a wide variety of elements and minerals. It is believed that because of the increased content of radioactive elements, a planet of this type should exhibit increased volcanic and tectonic activity, and its high gravity should prevent the formation of extremely high mountains and deep chasms. At the same time, the ratio of land to ocean on the surface of Kepler 452b should be different from that on the Earth. Consequently, chances are that this exoplanet may turn out to be a boundless ocean, dotted with archipelagos. If we leave the abstract figures for a moment and try to imagine what life might look like on this amazing planet, so similar to Earth and yet so different from it in so many ways, a truly fantastic sight will unfold before our eyes. The probable abundance of shallow warm seas allows us to expect a great variety of aquatic life forms, from the smallest to the most impressive. As for land, there are likely to be stocky trees with thick trunks and stalky herbaceous plants. Because the spectrum of the parent star in this system is close to that of the Sun, the color of the photosynthetic parts of local plants is likely to be familiar to us, green or bluish. We can also expect a variety of small animals with sturdy bones and strong muscles. Another course evolution might take is creatures with an external skeleton, like terrestrial arthropods. As for flying creatures, the opinions of exobiologists are divided. Some believe that high gravity will be an insurmountable obstacle to flight, while others suggest that the high density of the atmosphere will be the decisive favorable factor in this matter. In any case, we still have many years of research ahead of us before we can say with any certainty that this planet is indeed suitable for life. In terms of the vastness of the cosmos, our planet is just a small rocky fragment traveling at incredible speed through boundless emptiness. For billions of years, it has been orbiting the Sun, maintaining a distance of about 150 million kilometers. However, the true size of our system is much larger. According to modern concepts, its outer boundary, which is considered the far edge of the hypothetical Oort cloud, is at a distance of about 100,000 astronomical units. Beyond this boundary begins the vast abyss of the interstellar vacuum, space so rarefied that there is on average only a single hydrogen atom per cubic centimeter. The distances between the nearest stars in our part of the galaxy are a matter of a few light years, and a photon that has left the Sun can reach Proxima Centauri without ever colliding with a particle of matter. This vast void is a pervasive and integral part of the deep structure of the cosmos. It permeates the entire Milky Way, separating stars and planets, black holes and white dwarfs, super-dense pulsars and scattered nebulae. If you move outside the galaxy, you can see that it is surrounded by an even deeper vacuum. For example, between us and the Andromeda galaxy lies 2.5 million light-years of exceptionally rarefied space. This distance is so great that 25 galaxies like ours could fit in it, yet it is filled only with the deepest cosmic vacuum. And this is only a small part of the great cosmic abyss. The Milky Way, the Andromeda Nebula and the Triangulum Galaxy, as well as about 100 of their satellites, are bound together by pervasive invisible threads of gravity. This structure is called the local group and is a large cluster of cosmic matter about 10 million light-years in diameter. The local group, in its turn, is part of an even larger formation, but a relatively small galactic filament by the standards of the universe, called the local sheet. This flattened structure, consisting of several hundred galaxies, has a diameter of about 46 million light-years, and its thickness is roughly 5 million light-years. The sheet is also part of an even larger association called the Virgo supercluster. However, very close to the local sheet, outer space suddenly changes its appearance. Here, the usual colorful universe is harassed by a giant black abyss known as the local void. In fact, the local sheet is one of its walls, the other conventional boundaries being the Perseus-Pisces supercluster and the Pavo-Indus supercluster. At the same time, the void is divided into conventional parts by several rarefied galactic filaments, and wide passages link it into a single network with the neighboring Sculptor and Hercules voids. Due to the cosmological expansion of the universe and the gravitational influence of the surrounding matter, the volume of the local void is slowly increasing. At present, its diameter is about 150 million light-years, and the distance to the center is at least 70 million light-years. Meanwhile, the nearest edge of this cosmic void is located very close to the Earth, at a distance of about 3.2 million light-years. Due to this proximity, the local void occupies a significant part of our planet's night sky, about 40%. The main plane of the Milky Way, containing many bright stars and large nebulae, covers the central part of this region from us. Still, its edges do remain accessible for observation. In 1854, a dwarf spiral galaxy was discovered a little north of the constellation Hercules. It was dubbed NGC 6503. Later, with the advancement of observation techniques, it became known that it is located in the middle of the local void, and its distinguishing feature is the incredible multicolor appearance. The spiral arms of the galaxy are permeated with bright red clots of heated hydrogen, and shining blue nebulae are stellar nurseries. The center is obscured by clouds of cool gas and dust, which have a noble brown color. NGC 6503 has a diameter of about 30,000 light-years, and its distance from Earth reaches 17 million light-years. Due to the gravitational pull of the Virgo supercluster, this galaxy is approaching us at a speed of about 43 kilometers per second. It is believed that its gradual approach to the local sheet will eventually saturate its space with interstellar hydrogen, causing an increase in star formation. It is estimated that in a few billion years' time, the current number of young stars could double, and the small galaxy will shine with renewed vigor. The motion of NGC 6503 is a clear demonstration of how the voids are likely to have come about. It is believed that the foundations of the large-scale structure of the universe were laid in the first minutes of its existence, at the time of chaotic mixing of matter and energy. Cosmic cataclysms of incredible power shook the young universe, forming local compactions and voids. Subsequently, clots of matter became proto-galactic clouds, and areas of space of reduced density became voids. Over time, the pervasive influence of gravity intensified this contrast, pulling stars and cosmic gas into relatively dense clusters, making the space and voids even more rarefied. Observations show that the vast majority of galaxies formed between 10 and 13 billion years ago. In addition, no significant differences have been found to exist between the age of galaxies located in voids and those that form global filaments. This fact also confirms the modern theory of the formation of the large-scale structure of the universe. Meanwhile, allowing for the cosmological expansion of space, we can assume that with time, the local void will become larger and more rarefied, and the Virgo supercluster will gradually disintegrate into several independent groups. At present, it is an association of about 30,000 galaxies concentrated in a region of space with a diameter of about 200 million light-years. At the same time, the total mass of the cluster is about 1.5 quadrillion solar masses, which is tantamount to about 1,000 galaxies such as the Milky Way. The Virgo supercluster is partially contiguous with two other galactic superclusters, the Centaurus and Pavo-Indus superclusters. At the same time, its other side borders on a vast region almost devoid of matter. It is called the Taurus void and is one of the largest known cosmic voids. It is rather difficult to study this part of outer space. The reason is that most of the void lies in the so-called zone of avoidance, a sector closed off from us by the Milky Way plane. The bright stars in our galaxy outshine the fainter and more distant sources, and interstellar matter absorbs and scatters their light. However, thanks to infrared studies, we do have some ideas about the structure of this void. The diameter of this tremendous void is about 200 million light-years, and the distance to the center is about 150 million light-years. When observing the void, one is immediately struck by the remarkably clear boundary between between the relatively empty space and a bright cluster of galaxies located much further away. It is called the Perseus-Pisces supercluster and is one of the largest in this part of the universe. A transition this sharp is characteristic of dust clouds, even though infrared studies do not confirm their presence. In all probability, the clear boundary between the void and the supercluster is caused by gravitation, but the exact mechanism of their action still remains to be found out. Meanwhile, it is thought that the Taurus void, like most other cosmic voids, is not quite as empty as one might imagine. The way light passing through it is distorted suggests that this region may hide in its depths giant gas and dust clouds, the cradles of future galaxies. According to other hypotheses, huge masses of dark matter, the most mysterious substance in the universe, the properties of which are still not fully understood, may be contained inside the void. According to the most daring ideas, there are clots of antimatter or even more exotic matter with negative mass in the centers of cosmic voids. Nevertheless, despite their boldness, these hypotheses lie outside the boundaries of generally accepted scientific concepts, which makes it difficult to verify them experimentally. Currently, only 2 separate galaxies have been discovered tucked away in the space of the giant void. One of them, UGC 2627, has a spiral structure and resembles the Milky Way, while the second, known as UGC 2629, is an elliptical dwarf galaxy. Both objects are located almost in the heart of the void, at a distance of about 185 million light-years from us. The distance between them is small and is within a few 100,000 light-years. Perhaps there are other single galaxies hiding in the space there, but the Milky Way disk does not allow us to see them. Meanwhile, the Virgo supercluster, together with 4 other superclusters, forms a giant galactic filament called Laniakea. It contains more than 100,000 galaxies and stretches for more than 500 million light-years in space. Its gravitational center is the Great Attractor, a mysterious supercluster of galaxies located 250 million light-years from Earth. In its turn, Laniakea is part of a vast galactic stream, and further out, one can see that most of it is surrounded by a black abyss of unprecedented proportions. The light of distant galaxies is drowned in its emptiness, and even the mysterious and elusive neutrinos take billions of years to cross this cosmic abyss. To be honest, it is hard to believe that despite all the development of observational technology, such a gigantic void was noticed only 10 years ago. The year 2013. The University of Wisconsin-Madison. A team of astronomers led by Professor Amy Barger is working to determine the distance between galaxies. In the process, an unexpected and staggering fact is discovered. It turns out that Laniakea and most of its surrounding superclusters are enveloped by a cosmic void of unprecedented proportions. After making calculations, scientists discovered that its diameter exceeds that of any previously known void. The size of the discovered void turned out to be so enormous that several fundamental cosmological principles were questioned. It appears that the universe is much more elaborate than we imagined. The research done by Amy J. Barger, Ryan Keenan and Lennox Coey has led, in all likelihood, to one of the greatest astronomical discoveries of recent years. Their work has shown that our galaxy, along with its surroundings, is located in the middle of the largest supervoid known to science. It was named KBC, after the first letters of the discoverers' names. Observations show that the shape of the giant void is close to spherical, and its diameter may exceed 2 billion light-years. According to calculations, the Milky Way is located a few hundred million light-years from the conditional center of the great cosmic abyss, and about the same distance from its edge. The discovery of a giant bubble of emptiness surrounding Laniakea helped to explain the paradox that had kept scientists busy for many years. The fact is that all galaxies in the universe are gradually floating apart due to cosmological expansion. Measuring the speed of this motion allows us to calculate the so-called Hubble constant, a fundamental physical constant characterizing the rate of expansion of space. However, if we take the galaxies closest to us to calculate the Hubble constant, it turns out that the rest of the universe is expanding too slowly. On the other hand, if we take distant objects as the basis, the Milky Way's surroundings are moving faster than they should. The discovery of the void has accounted for a lot. The fact is that the galaxies inside it, including the Milky Way and its neighbors, are constantly experiencing additional gravitational influence from objects outside the void. This creates an additional force that gradually stretches our cluster in different directions. It is also surprising that the KBC void is so huge that it comprises not only superclusters of galaxies, but also other voids. For example, the local void, as well as the torus void, are part of its structure. It turns out that compared to other voids, even though KBC looks large, it isn't quite so empty. Nevertheless, according to calculations, even this void is just a barely noticeable dark spot against the background of the observable part of the universe, the diameter of the latter reaching 92 billion light-years. If we look at the global map of the universe, we will see a lot of dark spots on it, close to the KBC void in terms of their size. Most of them easily fit within the framework of modern physical theories, while others show surprising and strange properties, difficult to explain from the point of view of science. And one of the most noticeable riddles of this kind in space is the Eridanus supervoid, also known as the CMB cold spot. It is estimated to have a diameter of 500 million to 1 billion light-years, and it lies at a distance of between 6 and 10 billion light-years from the Milky Way. This means that this formation is one of the most extensive elements of the large-scale structure of the universe. The void is located in the southern hemisphere of the Earth's sky and occupies an impressive area on it, several times larger than the full moon. However, it is impossible to see it with the naked eye. The CMB cold spot is visible only with the help of special telescopes that study the cosmos in the microwave spectrum. Thanks to these, astronomers have discovered that within the spot, relic CMB radiation of the universe is about 70 microkelvin colder than the metagalactic average. This deviation is nearly 4 times as intensive as the strongest anomaly previously recorded, and its gigantic size makes it a truly enigmatic object that requires extensive study. It is now believed that relic CMB radiation traveling through hundreds of millions of light-years of deep vacuum is gravitationally influenced by distant galactic superclusters. This causes the pervasive echo of the Big Bang to lose energy, making the CMB cold spot appear cooler in images than its surroundings. Nevertheless, this effect cannot fully explain the excessive cooling of relic radiation. According to calculations, the attraction of external galaxies can account for only a quarter of the observed deviation. It is assumed that the remaining 75% of the effect may be due to the impact of hypothetical dark matter or dark energy concentrated in the depths of the void. However, it is going to take a while before we can truly unravel this cosmic mystery. It is well-nigh impossible for the human mind to realize the staggering dimensions of the universe. It conceals infinite abundance of mysteries and secrets, countless diverse objects, and boundless expanses of unknown space that are forever hidden from keen observers' eyes. We can only guess what other unique anomalies lurk in the dark depths of space, and it is quite possible that one day they will overturn our ideas about the universe and our place in it.